To study the fundamental nature of matter, physicists must accelerate charged particles to extreme energies. In the simplest model, this is achieved by applying a static electric field to push an ion in a straight line. The logistical limit of this linear approach is scale. To reach required velocities, a straight vacuum tube must span several miles. The engineering challenge is to generate this continuous acceleration within a compact, manageable physical footprint. The cyclotron was developed as a direct response to these physical space constraints. We can see the engineering scale of these early machines in this archival photograph, which shows the housing required for the internal components. This design utilizes a combination of electric and magnetic fields to manage the particle's trajectory. These are configured as crossed fields, where the electric and magnetic fields are positioned perpendicular to one another. This configuration forces the particle into an expanding spiral, allowing it to traverse the same physical space repeatedly as it gains velocity. Understanding the cyclotron requires breaking the machine down into its core components, starting with the internal housing. The interior contains two hollow D-shaped metal boxes called Ds, separated by a narrow central gap. When a charged particle enters a D, it encounters a uniform magnetic field oriented out of the plane of the machine. Because the magnetic force acts perpendicular to the particle's motion, it is diverted into a circular path. Inside these hollow metal structures, the particle experiences electrical shielding, meaning it is protected from outside electrical forces while in mid-orbit. In this system, the magnetic field is used strictly for steering and containment. It forces the particle back toward the gap, but does not contribute to its speed. Acceleration only occurs in the narrow gap where the shielding from the Ds is absent. As the particle crosses this space, an electric field provides a push, increasing the particle's kinetic energy. This field is powered by an oscillator. Each crossing increases the particle's speed, which in turn increases the radius of its next orbit. To ensure continuous acceleration, the oscillator reverses polarity every time the particle transitions from one D to the other, so the field always pushes the particle forward. Because air molecules would cause collisions and energy loss, the entire assembly is housed in a vacuum. This creates a self-contained engine. Magnetic fields handle the steering, an alternating electric field provides the thrust, and the vacuum removes resistance. This design introduces a potential conflict. As the particle speeds up, the physical distance it must travel in each orbit increases. If the path grows longer, we have to determine if the particle will still arrive at the DAB in sync with the oscillator's fixed timing. In a uniform magnetic field, the frequency of a particle's revolution is independent of its velocity. This is the cyclotron frequency, F sub c. As the formula shows, the frequency depends only on particle charge, mass, and magnetic field strength. This leads to the resonance condition, where the frequency of applied voltage is tuned to exactly match this natural cyclotron frequency. The increase in velocity perfectly compensates for the longer orbital path, ensuring the particle hits the gap at the exact microsecond the electric field flips. The particle continues this spiral until it reaches the outer limit of the Ds and is directed toward an exit port. This formula allows us to calculate the particle's final kinetic energy at the moment of exit. The energy output is determined by the particle's charge, the magnetic field intensity, and the maximum radius allowed by the machine's physical size. We can also verify this by multiplying the voltage by the total number of times the particle crossed the accelerating gap. In a large-scale facility like this one, the resulting particle beam is then utilized for high-energy research. Because energy is limited by the physical radius and magnetic strength, reaching higher levels requires the construction of increasingly larger accelerators. While the cyclotron's geometry suggests it can be scaled indefinitely, the design eventually encounters a limit imposed by special relativity. This equation for the orbital time period, t, shows that the time required to complete a circle is directly proportional to the particle's mass. Classical mechanics treats mass as a constant, but this assumption fails at high velocities. As a particle approaches the speed of light, its relativistic mass increases according to this formula. This mass increase causes the orbital period to lengthen, meaning the particle takes longer to complete each revolution. This lag causes the particle to arrive at the gap late, falling out of sync with the oscillator and ending the acceleration process. This relativistic limit is most visible when attempting to accelerate very light particles, such as electrons. Because electrons have such low rest mass, they reach relativistic speeds almost immediately upon entering the machine. Their mass increases so rapidly that they cannot maintain a consistent orbital frequency. This rapid mass variation makes the cyclotron unsuitable for light particles, as the resonance condition fails nearly instantly. To solve this, physicists developed machines like betatrons and synchrotrons, which can adjust their fields dynamically to compensate for relativistic effects. While the cyclotron is the foundational tool for heavy ion acceleration, reaching higher energy scales requires engineering that accounts for the relativistic effects of high-velocity physics.